Group configuration. Okay, what is group configuration? And let's put down today's date. Today is the 15th of December, 2015, 12/15/15. Okay. So, group configuration. Group configuration is just the electron configuration that all elements in a group share. So, if we talk about group 1, they all end with what? Something S1. And if the period is equal to main energy level, which it is, and the period is equal, we refer to main energy level as N, then group 1 all ends with NS1. So easy for me to say. For something that's in the third period, what would its configuration be? Well, it would be, for in the third period, in the first group, it would be, and I'm going to even skip off the noble gases, it would be 3s1. And I think you were answering a different part of the question. That's okay. If it's in the sixth period, some noble gas plus what? 6s1. So it's whatever they all end with, basically. That's the group configuration. Yes, ma'am?
Can you do the D block?
I can. Because those are weird, huh? So let's do something in group, so we'll say group 14. So first of all, what's group 14's normal group configuration? So some noble gas plus what? Okay, so NS2 for sure, and N minus 1 D what? We sometimes do that. So group 1, group 2, I'm sorry, gosh, not group 14, group 4, duh. Nobody even called me on that. Group 14's P block. You're all still so happy about the no test that you can't even... 2, yeah. You know what, and this is where it comes down, your book does it this way. I don't care if you write it, if you flip them into main level order, or if you write, yeah, I'm fine with you writing it as NS2 N minus 1 D2. I don't care which one you write first.
So the N minus 1 is defined in the
What?
The N minus 1 is defined in the energy.
N minus 1, it's the D that's filling is 1. It's on the next level down from the highest main occupied. Other questions? Group configuration. You want to do another D group configuration? Okay. Let's do group 4, 5, 6, 7, 8, 9, 10. Group 10. So some noble gas plus what? NS2, she says. And then what? N minus 1, D8. So for the P block, let's do group 15. So what would be the group configuration for group 15? Some noble gas plus what? NS2? Well, not for all of group 15, but possibly. So, because if we're in the first 3 periods, there is no D. So typically, and that's a great point to talk about. Typically, when we look at the P block, we don't think about the things that are down below group 4. When we talk about group configuration for them, we really only worry about the S and Ps. because that's what behaves as a valence electron. So when we're talking about group configuration, we're mostly talking about the things that act as valence electrons. In the D block, remember that those D electrons can act as valence electrons. They do leave, they travel. But in the S and P block, we really just talk about the S and P electrons for their group configuration. So for group 15, NS2, NP3. Make sense? What about group, 17? Subnoble gas followed by NP5. And, notice group 15 has got 5 valence electrons. That's what we talk about as having 5 valence. Group 17 has 7 valence electrons. So doing that, you should be able to go back and forth really fast, really easily from the group configuration to how many valence electrons they have. It's less important as you go forward in chemistry that you understand that, 2 are in the S and 5 are in the P, and it's more important that you understand immediately, 7 valence electrons, it's going to gain 1. It's more important that you understand, we very often call it oxidation state, how many electrons it will gain or lose, which orbitals that it's in, yes, but that's more important. So there was the one question on the homework where we were talking about the D block, and there are some where it's like NS1D3, and you would think it should be NS2, and then a D2. There are some weird exceptions. I don't care that you know them. I do not care that you know those. And those are found experimentally. Those aren't something that you can predict necessarily. I would just ignore those. I want you to understand the total number of S and D electrons in the D block, and know that the total number of S and D, when you add them together, are really the ones that they tend to give up or gain. So hence why you can have, has anybody here seen the movie Erin Brockovich? It's okay. It's a good movie, and there's some interesting science in it because there's a chemical compound. Do you remember what it was? It's chromium-6, and when we start getting into compound formation in the next chapter, or the next two chapters, chromium forms a +6 ion. Well, I thought things didn't really give up or gain more than 2 or 3 electrons. Well, the metals can make some really weird ions because they have that whole D block that kind of starts to act as valence, and they do a different form of bonding called metallic bonding, and we'll talk about that. So that's really all I care that you know in the D block. I don't care if you know which ones are exceptions to the rule. Understand that the total number of S and D is the group number, and it's, though I can't think of a single example where they give up all. Well, vanadium forms vanadium-4, so it gives up 1, 2, 3, 4, 5. It gives up 4 of its 5 valence electrons. So anyway, yeah, that's less important though. Other questions? Oops. Okay, this is the one where I use that hill and a rock metaphor, or a bowling ball, Gesundheit. When we talk about ionization energy, despite the fact that ionization is just the process of making an ion, when we talk about ionization energy, we're talking about the energy change when you strip an electron off an atom. The change when you add an electron to an atom is electron affinity. What you really need to take out of that is electron affinity is all about adding electrons. It's never about taking them away. And if you think about what is affinity in everyday colloquial speech, I have a tremendous affinity for chocolate chip cookies and avocados. Yes. An affinity is a liking for. So, you can think of all the things in your life that you have an affinity for. Electron affinity is basically how it's the amount of energy change you see in an atom when it takes on an electron. And the metaphor that I used here was the one of like the freezing water. So if we look at solid, liquid, gas. We're not even going to talk about plasma. If we put a liquid on a plant and let it freeze on the plant actually doesn't freeze, because this amount of energy here, the difference in the energy level of the water molecules when they were in a liquid state versus a solid state, that amount of energy is given off to the environment, and the environment happens to be the plant that it's sitting on top of. So we have this difference in energy, and this difference in energy is the difference in the energy of the water molecules. What kind of energy do water molecules have? Multiple different answers here. Well, we could say thermal. They have if it's above absolute zero, they have thermal energy. Really what that thermal energy is, it's kinetic energy at the molecular level. You know that molecules are moving all the time. At any temperature above absolute zero, molecules are moving, and so they are moving more slowly when they're a solid than when they're a liquid. So the change, the difference there, is given up to the environment, is given up to the plant. What?